So, hello everyone, welcome to uh, today's live interactive session on geology and soil mechanics. So, as you all know, today is the 12th week, 11th, 11th, right? Or I forgot, 10th week, I think. Sorry. Today is the 10th week, probably. The 10th week lecture or the discussion session that we are going to have. And we have 3 more discussion sessions that we'll be having. So 11th and 12th discussion session will be 2 hour long, and we will be having one more extra discussion session that is on the so after that we'll be having the 11th discussion session on 5th April. Then we have another one on 12th April, and we will be having one summary session on the 13th of April. Okay, that will be of 1 hour duration. So we will be having a summary session on the 13th. Before that, the next week we will be having on the 5th we will be having 11th discussion session, and on the 12th April we will be having the 12th discussion session. Alright, and the summary session will be on the 13th. Alright, okay. So let us start today's session. So as you all, if you remember from the previous session, we dealt with the shear strength topic, right? We studied we solved problems regarding the shear strength chapter, in the shear strength chapter, where we studied about the different tests like the triaxial test, and we solved some problems regarding those too. Okay, and we also learned about the pore pressure parameters. We saw what are pore pressure parameters and how can we actually find out the pore pressure parameters during the triaxial test, and why are they actually important to us. All those things we studied in the previous session. And in today's class, what we are going to do is that we are going to start a new topic. Okay, we are going to start a new topic that is our that is the topic of earth pressure theories. Okay, so you might have already gone through all the things that were taught in the class, right? So we will be just revising a bit all these things. Okay, we will be revising a bit all these things, and after that what we are going to do is that we are going to solve some problems. All right, so before we begin, just give me, let us pull out the contents. uh, just give me, okay, just a second, huh? Okay, so what do you mean by earth pressure? Okay, what do you mean by earth pressure? Okay, earth pressure is what? So say you have a retaining wall. Say a retaining wall. So retaining wall. Why do you construct retaining wall? We construct retaining walls to retain soil, right? We construct retaining walls. We construct retaining walls so that we can retain soil. Okay, so these are soil retaining structures. Retaining walls. So what happens? Say we have a retaining wall and we have a soil. So there is a tendency that soil would exert a pressure on the lateral pressure on the wall, right? So we have a wall, and we have some soil filled there. So what is going to happen? The soil is going to exert some pressure on the wall, right? So that is the earth pressure, that is called the earth pressure. So mainly there are three types of earth pressure. One is the earth pressure at rest, there is the active earth pressure, and the passive earth pressure. So what is a earth pressure at rest? Earth pressure at rest means that, say you have a wall, right, and you have a soil field here, and what is happening is that the there is no movement of the wall. Okay, so say you have a bridge apartment, right? So say you have a bridge, right? So here you have the bridge like this, and here is the bank, river bank. So here in the river bank you have some structure here, and this is fixed at the top, and as well as it is fixed at the bottom, right? And here you have soil, here you have soil. So in structures like this, what happens generally, this is the case of earth pressure at rest. So as the retaining wall is fixed at top and bottom, it won't move. So in that case, whatever earth pressure the soil is exerting on the wall, that is earth pressure at rest. Okay. After that we have active earth pressure. So what is active earth pressure? Active earth pressure means that there is a tendency for of the wall to move away from, so this is the soil field, so there is a tendency of the wall to move away from the field. Okay, there is a tendency of the wall to move like this, away from the field. So in that case, whatever earth pressure that the soil exerts on the wall, that is the active earth pressure. And the passive earth pressure is nothing but opposite of that. Opposite of that means the tendency that the soil is actually the wall is actually moving this side into the soil. Okay, that is the passive earth pressure. Okay, so you might be wondering how passive earth pressure, at what conditions passive earth pressure takes place. That is when, say, you have soil like this, you have retaining wall like this, and again this side also you have soil, and here also. So there is a tendency that the retaining wall would actually move like this, right? So if you see in this portion, what is happening? In this portion, the the wall is moving away from the soil here. So what will happen? Whatever earth pressure that is active here, that is nothing but the active earth pressure. Okay, and in this side, what is happening? And in this side also, what will be having is that. So uh, up to here, okay, up to here we will be having active earth pressure. Then here in this portion, we will be having passive earth pressure. Why passive? Passive because in this part the wall is actually pushing into the soil. So in this part we will be having passive earth pressure, and again in this part we will be having the active earth pressure. Why active earth pressure? Because the wall is moving away from this soil. Okay, understood? So in the upper portion it will be active zone, this down it will be passive zone, and again this side it will be the active zone. Alright, so like this generally it happens. So active earth pressure, you can see this is the wall here. Okay, this is the wall, retaining wall, and what is happening is that the retaining wall, it's getting deflected. Okay, getting deflected away from the soil. So due to that, what happens? Due to that deflection, what happens? There is a earth pressure. Okay, draw it like this also. There is an earth pressure, so the opposite reaction is actually drawn here. So actually it's like this, right? So earth pressure that is acting, okay, into the wall. The earth pressure is acting into the wall. All right. And how that earth pressure that actually happens, that develop, that mechanism is actually uh, developed using this sliding wedge theory. So Rankine actually gave this sliding wedge theory, where he said that the soil actually fails at a soil wedge actually fails at an angle of 45 plus 5 by 2 degrees with the horizontal. That failing wedge actually slides down. The tendency of sliding down of that failure wedge actually exerts a earth pressure into the wall. Okay, and so this is nothing but the failure plane. Okay, this is the failure plane. Okay, so the earth pressure the soil wedge tends to slide down, and so the resisting shear, the shear strength of the soil, or the resisting shear, whatever soil strength the soil has, that is going to resist. Okay, that is going to resist this sliding. Okay, so there is a mobilization of shear strength along that shear stress, mobilization of shear stress along that failure wedge, right? So you can see here this P is nothing but the active earth pressure. This makes an angle delta. So that delta is nothing but the friction angle between the soil and the wall. Okay, there is a friction angle between the soil and the wall. Okay. Now let us see the case of the passive earth pressure. So passive earth pressure, as I said, when there is a tendency of the wall to move towards the field. At that time, whatever earth pressure is acting on the wall, that is the passive earth pressure. Okay, that is the passive earth pressure. So in that case, what will happen? There is a tendency of this failure wedge to slide up. So the mobilization of shear stress is like this at the failure wedge. And in this case, the failure wedge actually makes 45 minus 5 by 2 angle with the horizontal. Okay, and this W here is the weight of the failure wedge ABC. Okay, it's the failure wedge. Okay. So, as I said, say you have a wall like this, right? So there is a tendency for the wall to bend like this because soil is up. Soil is like this here. Or say here also you have some soil. So what will happen in this region? We have the active, and this region we have the passive. Okay, and if the rotation is about this point, okay, this is the rotation about this point. Now if the rotation is about this point, if the rotation is total complete rotation like this, then the case will be something else. Okay, so it depends how much deflection the wall is having. Okay, okay. Now next, what we have is the, we can see a figure where we have plotted the earth pressure with the movement, so towards the field. So you can see mobilization of the passive earth pressure, we need a large amount of deflection towards the field. But compared to that, the active earth pressure, we need a lesser amount of deflection away from the field. Okay, so you can see this is the value of the PA. So PA is quite less. Then we have P naught, that is earth pressure at rest, and maximum we have the PP, that is the passive earth pressure. So the value of passive earth pressure is the maximum, minimum is the active earth pressure, and between we have the earth pressure at rest. Okay, so this side is towards the field movement and this side is away from the backfield. Okay. Now let us see this. So Mohr circle representation, Mohr circle representation of the earth pressures. Okay, Mohr circle representation of the earth pressure. So you can see at rest. Okay, so when the soil is at rest, okay, when the soil is at rest, this this much is the vertical pressure that is acting. So say this, okay, so this, so this is the vertical that is acting, and at rest you have the what, you have the earth pressure at rest that is acting. So vertical stress, if we take a soil mass in soil cube, so we will having a vertical stress that is acting on the soil. So say you have a soil mass, sorry, say you have a soil mass like this. Okay, you take a point here. So at any point at rest you will be having a vertical stress that is acting, and then we will be having a horizontal stress. So at rest, at horizontal stress is nothing but the earth pressure at rest. So this, obviously this one is greater than this one. So if you want to plot in Mohr circle, this one will be sigma 1, this one will be sigma 3. So you can plot, so you will get this circle. Okay, this circle. Now in the case of active earth pressure, so in active earth pressure what happens? Active earth pressure also same, vertical, and that time active earth pressure will be active, right? Active earth pressure. So in that case, this active earth pressure is further lesser than P naught. So what will happen? So as the deflection, as the deflection of the soil, of the wall increases, this circle will actually start on growing on the left hand side direction. Okay, then and finally it will touch the failure envelope. Okay, so this is the failure envelope. Finally it will touch the failure envelope, and the point here, this point will be nothing but the P. Okay, similarly, if you want to see the passive phase, so in passive case also this PA will be PP, so and PP is greater than P naught, right? So to say, so when the wall starts deflecting towards the backfield, so slowly, so in first stage it will attend this circle, then it will attend, finally attend this is the final failure stage, because this circle touches the failure envelope. So that state, that will give us the PP. Okay, that will give us the PP. So that PP is obviously greater than the vertical stress. So here you can say this is the sigma 1, and this, in this case, this is the sigma 2. Okay, now this angle, if you measure, this angle is nothing but 45 minus pi by 2, and this angle, if you measure, this is nothing but 45 plus. Okay, so that's how we get 45, not this angle, sorry, just easy to draw. So this angle is not 45, and this angle is the horizontal, right? So this plus, okay. Now earth pressure at rest. Okay, so how to get the coefficient of earth pressure? So you have, say you have a soil mass. Okay, so you have the vertical stress acting. Okay, now what is this? So this is some coefficient times this. Okay, vertical. Okay, this is some coefficient times this vertical stress. The earth pressure at rest or any lateral earth pressure is times some coefficient times the vertical stress. Right? So how to get this earth pressure coefficient? Now the horizontal strain can be written like this: 1 by E horizontal stress minus mu into vertical plus horizontal. Right? This can be written. Now at earth pressure at rest means what? This horizontal strain is 0. There is no movement of the wall, no movement of the soil mass. So the strain is 0. So from there you can write. So what is this? This is nothing but earth pressure at rest is nothing but K naught into V, where this K naught is nothing but mu into. So this earth pressure coefficient of earth pressure at rest is nothing but this. Okay. Now, Rankine's earth pressure theory for cohesionless soil. So what Rankine considered is that the cohesionless soil, that's why you can see that the failure envelopes that are drawn. Okay, so this is a failure envelope, this is a failure envelope, right? The failure envelopes that are drawn that make zero intercept on the shear stress axis, right? Now, Rankine gave a earth pressure theory, so he made some assumptions. So first assumption was that the soil is cohesionless. Second, he said that there is no friction. Okay, there is no friction between the wall and the soil. Okay, so frictionless soil wall interface he considered. All right, then he also considered that the failure line or the failure plane is a straight line or a wedge. The failure is actually a wedge. Okay, straight line failure, whatever we assumed in the initial slides. Okay, so he assumed all these things, right? So this one we already saw in the previous slides. Okay, so we have the two more circles. This is the passive case, this is the active case. Okay, so here you can see the inclination with the failure planes are given. Okay, this is the PA, this one will give you the PA, this will give us the PP. Okay, now how to get this coefficient of earth pressure for active and passive case. How to get Ka and Kp? We cannot we already find out mu by 1 minus mu that we got. Now how to get the coefficient of earth pressure for this case? How to get the coefficient of earth pressure for this case? Okay, how can we get it? That is the question. How can we get the coefficient of earth pressure for active and passive phase? That how can we get? So, if you recall, write it here. So since we are dealing with the cohesionless case, so C is 0, this term will be 0. Now for the active case, this is our mode circle, right? So here sigma 1 is what? Sigma 1 is nothing but Pa, and sigma 3 will be nothing but the vertical stress. So that is also nothing but Pa active, and this is nothing but the vertical. Sorry, sigma 1 is the vertical, right? Sigma 1. So this is sigma 1, right? And this is sigma 3. Is it? So sigma 1 is vertical, sigma 3 is, what I can write, P is equal to or it is P is equal to, so this is nothing but Ka. Also write this is like this. Okay. Now what about the passive case? In passive case, same. So in passive case, sigma 1 is Pp. So okay. One more thing, if you see, you will see that K is equal to, right? Okay, and there is a term n5. Sometimes n, this term is also known as n5. Okay, n suffix 5, right? Okay, so this is how we get the coefficient of earth pressure for active case and for passive case. All right. Now let us see for these conditions. At this condition, how the variation of earth pressure is going to happen. So dry, submerged, and partially submerged conditions. So first condition is what? So this is the wall. Okay, and this is the wall, and this soil is dry soil. Okay, so if the soil is dry at any depth z, okay, at any depth z, any depth z, the active earth pressure is what? Ka into the vertical. The vertical is sigma into gamma into z, right? Vertical stress into k. What is the passive? Kp into gamma into z, right? So what we will be getting is that we will getting a triangular variation in both the cases. We will getting a triangular variation of stresses. So now how to get the total stress? Total stress is half k into gamma h into h. So we will be getting half k gamma square. So this will give us the total stress, whether it is P, capital PA or PP. Okay, this will give us the total stress. This are okay, total lateral load that is acting. Okay, okay, this will be in force terms, Newton or kilonewtons. So this is the lateral load. Okay, and this is the pressure. The pressure and total load you can find out by finding out the area of the track. Okay. Now, if the soil is completely submerged, then what we are going to do is that we are going this gamma you are going to use it as the submerged unit first. Okay, so the earth pressure will be again having a triangular variation, but at this time this will be Kp into gamma submerged into the height. Okay, plus along with that what we need to add is that we need to add the due to water. So water, you know, Pascal's law, it exerts equal pressure in all directions, right? Hydrostatic pressure, because it is hydrostatic pressure, so that we also need to add. So that is nothing but gamma w into h, right? So you need to get the water into the height. So these two you need to add. So always we need to sum these up. Okay. Okay. So here active case is shown. Same will be the case for passive case also. Just it will be, this one will be replaced by PP. Okay, KP. Here active is shown, so I have done a KP. So other things I will be same. So don't forget to add this part. Okay. So this all these things will get more clearer as we solve the problems. All these things will be more clear. Now what will be the changes if we have a partially submerged condition? Okay, so we have water table at some depth, some height, and also you can see we have a surcharge q that is acting on the top of the soil. We have a surcharge. So first let us see. So k and kp, this all the both the things will be same. So just it is for ka it is shown there, whatever k. Okay, just you can think k. K. K is K. It may be either K or KP. Now, for the surcharge, the lateral stress is nothing but K into Q. Okay, that will be nothing but triangle rectangular variation, because at all heights Q is acting. We show that Q is acting. So horizontally it will be K into Q at all heights, right? It is nothing but a triangle rectangular variation. Now for this part, for the upper portion, for this portion which is dry, so same for, so for this, the upper portion, what we are going to have, we are going to have first, we are going to have a triangular variation. And what is going to be this? Let's say this one is H1, right? So H1 into K into gamma. Right? So let me write it like this: K into gamma into H1, right? Gamma. Dry your whatever unit weight, total unit weight. K into gamma into H, total unit weight. Gamma is the total unit weight. Okay. Now, for the lower portion, it is submerged. So what we are going to is, we are going to add submerged. So at this height, this is the thing. But at lower point, what will be the yeah? So K into submerged unit weight into what is the height, total height, H1 plus H2, something like that. And in this height, it will be this variation will be like something like this. Okay. Okay, so you can see the slope has become a little bit gentler slope, because here the slope is this gamma. All right, so this is how we are going to do it. All right, plus obviously for the lower portion, we are going to have the water, so water pressure. So the lower portion, we are going to have the water pressure like this. Okay, gamma W into H2. Okay, it's nothing but the water pressure. So all these you need to add up total to get the total answer. Okay, so we will see this as we solve the problems. We will see that it is becoming more clear. Okay. Now let us come to the case of cohesive soils. Okay, cohesive soil means what? We have some C value. Initially, the before whatever we did, it was for cohesionless soil. Now let us see for cohesive soil. So say the molecular of failure equation, we will write past Federer-Mellab's equation. Right? Okay, so as I said, this term can be written as what? This term also is called n phi, right? N phi. So what we will be writing in terms of, let us write in terms of n phi. Okay, so let us write in terms of n phi. Okay, so we will be writing in terms of n phi. Okay, now in the case of active, this is what? This is sigma v, this is PA, so if we do PA, right? So here you can see the first part is same like before. Here the pressure, the first part is same, nothing but K into sigma V. But now you are having this another part, this part. So when height is 0, okay, when height is 0 means at top here, when the depth is 0, when Z is equal to 0, sigma V is 0, so the first term will be 0, isn't it? The first term will be 0 as sigma V is 0, the first term is going to be 0. Okay, but you can see there is a second term that will exist there, that is negative, this part. So that part if we draw, that part will give us this triangle. Now at this point you can see the earth pressure is 0. So that point, that depth at which earth pressure is 0, that is the Z naught depth. So if we equate this equation to 0, we can find that Z naught. Okay, we can find that Z naught depth. All right. So if we write this one, K gamma Z naught minus 2ic 0. K into gamma. That will give us Z naught. And now below Z naught again we will have the same this variation. Okay. Now see at the top portion, the this is actually stress is actually negative, right? This portion is negative, right? That is stress is actually negative. So negative, so that due to that what happens, sometimes some tensile cracks develop. Okay, so tensile cracks develop on the soil. So what happens is that, okay, this is the wall, so some tensile cracks develop like this. This is the soil, this is the wall, some tensile cracks develop. So if tensile cracks develop, then this triangle, the below portion whatever, so top portion what happens? The top portion, this part nothing will be acting. It is not attached to the wall, right? So no stresses will be acting on the soil on the wall. So the area of the bottom triangle, so this bottom triangle will give us the total earth pressure. Well, that bottom triangle is going to give us the earth pressure. Now what if, so this is the case of tensile cracks develop, but what if tensile cracks do not develop? If tensile cracks do not develop, if tensile cracks do not develop, what is going to happen? This and this portion, they are going to cancel out each other, because positive negative they are going to cancel out. So the area of this bottom trapezium, that is going to give us the earth pressure. Okay, the area of the bottom trapezium, so this trapezium, and this is gamma h and phi. This is going to give us the, this is 2ic, right? So this area of this trapezium is going to give us the active earth pressure. Okay, so these things actually we have to keep in mind. Okay, what condition the soil is, what soil is it, whatever, how it is submerged or not, or that is dry, okay, tensile cracks are developing or not, all these things we have to keep in mind while we calculate for the earth pressures. Okay, so all these things we have to keep in mind. Now let us see the case of passive pressure. Okay, now let us see the case of passive pressure. So again we will just write the right. So in that case, this is the passive pressure. So this also I can write N by Kp. Okay, so N pi is equal to K, equal to 1 by K. So you can see here in case of passive, we have this part that is there. So that is nothing but that will be like an extra, what to say, extra. This you can assume like an extra surcharge that is active. Okay, so that will be there throughout. Okay, so at any depth you will have a, from this part you will be having this triangle, along with that at all heights you will be having this. This is yc root over n pi, and this is to kp. Okay, gamma into h into. All right, so this is how that the variations actually differ in case of passive case, in case of active case, in case of cohesionless one, in case of cohesive. Okay, now now let us see this. So so what if, okay, so what if the backfill, the backfill that we have, that backfill is not straight, the backfill is actually inclined at an angle of beta. Okay, the backfill is not straight, rather the backfill is inclined. In that case, what we are going to do, in that case what are we going to do? If the backfill is inclined, not straight, if the backfill is inclined, in that case there are going to be some, so everything is actually same. So only change is that this pp, now this of the failure wedge, the whole failure wedge, that this whole triangle, whole this earth pressure triangle, we assume that it is inclined at angle beta. Okay, so this PA will be nothing but inclined at an angle beta. So before it was acting straight, so now this PA will be inclined at an angle beta. Okay, okay, but in this case also remember that you are assuming the soil is, so the friction between the soil and the backfill is 0. If the friction coefficient changes, there will be some more changes. Okay, so in case of an inclined backfill, so this is what, this is the expression for Ka, and this is the expression for K. Okay, so the K and Kp expressions are going to change in that case when the backfill is inclined at angle beta. So and the expressions are given here, K and Kp expressions are given. So by putting beta equal to 0, you can check if you are getting the original values of K and Kp. Okay, that is tan square, this tan square 45 plus 5 by 2, or tan square 45 minus 5 by 2. Those who are getting or not, you can check by putting in these two equations. Beta is equal to 0. Okay, right. So this was these are all the basics from this part. Okay, so these are very easy. Actually, this chapter is not that tough. It's quite easy. So just you have to pay attention to what the question is asking. Okay, whether it is asking for active earth pressure or passive earth pressure, or what conditions the soil is in, whether it is dry or submerged or partially submerged. Okay, whether you have surcharge. Okay, whether the soil is cohesionless or cohesive. All these things you have to pay attention. Okay, otherwise there is no chance that you will make mistake. Okay, otherwise it's very easy. Okay, so let us start solving the problems. Okay, so first question you can see here, a 15-meter high rigid retaining wall with smooth vertical back retains a mass of moist cohesionless sand with horizontal surface and following properties. Compute the total lateral earth pressure at rest and its location. The total lateral, so earth pressure at rest you need to do. If subsequently the water table rises to a ground surface, determine the increasing earth pressure at rest. Okay, so initially the earth pressure, the soil is moist, but after that what happens, the water table is rising to the ground surface, that means the whole soil is going to get submerged. In that case earth pressure is going to increase, that also you need to find out. So this we will see here that due to this water, if the soil, bacterial soil is submerged, the earth pressure increases by a large extent. Okay, so this is very important. So while we design retaining walls, we provide some weep holes in the wall so that the water is able to drain out. Okay, or some filter arrangement we made between the soil and the retaining wall, so that filter and drainage arrangement, so that the water actually drains out. So if water is actually gets retained in that backfill soil, it generates a huge amount of lateral earth pressure. Okay, that is actually detrimental to the safety. Okay, so sometimes what happens, if the soil gets submerged, it generates a huge amount of earth pressure, and that earth pressure can result in the failure of the retaining wall. So we need to provide some proper drainage so that the water drains out from the. Okay. So we have this wall. So this is meter. Okay, and then we have a back picture. Now it is asked to us to find out the earth pressure at rest. So again, triangular variation we are going to have. Right, in the first case we are going to have triangular variation in this what is this? K naught into gamma into 15. Okay, so P naught total will be half K naught gamma h square, so half 0.45 this will come out as per meter length, so kilometer per meter the wall. Okay, now this is the first case. Now what if the soil is submerged? Okay, water table rises to the ground surface with the soil getting submerged. So in that case, so what is submerged unit weight? Moist unit weight minus. So in that case, what is going to happen? So this is the wall. K naught into gamma submerged into height, and after that, with that, this water will also get added, right? Into each. Okay, so P is P1 plus P2. P1 is half K square, right? So calculate this, be approximately 1438. Okay, so what is the increase? Approximately 6. You can see it increases by large amount. Okay, due to the water, the presence of water, the earth pressure is getting increased by a large amount. Okay, okay, just a second. Okay, just see this question and try if you can solve this. So this is also same. A retaining wall 10-meter high retain a cohesionless soil with an angle of internal friction 35 degree. The surface is level with the top. There is not inclined backfill, straight backfill. The unit meter of the top 3 meter is 1.6 ton per meter cube, and the rest 2 meter is rest is 2 ton, rest 7 meters is 2 ton per meter cube. Find the magnitude and point of application of an active thrust. Okay, so just try to find this out, quite simple, very easy, same like previous only, but here this is the active case and the unit weights actually differ at the top level and the bottom level. The rest everything is same. Just try to solve this. Just try to solve. So we have a retaining wall. Okay, so we need to find this, calculate this. So also you need to calculate the total active watt pressure, also the point of application. Okay, at what point that is actually active. So first what we can do, let us find out Ka. Should be 0 point. Okay, all right. Now let us come here. Okay, so the first top portion, top 3 meters This is what? This is 16 into 3 into, okay, here we have, okay. What about here? So at the bottom, so this part, this is nothing but 27. Alright, understood? And this part, so this is, okay, and this will be, okay. This one is, this one is same 13. Right? So now what we can do, we can divide, okay, divide this in 3 segments. 1, 2, 3. Okay, so here we can write P1, P2, P3. Okay, now what is total? So total, my total PA will be P1 plus P2 plus P3. Right? P1 plus P2 plus P3. Out of that, P1 is what? Half into 13 into 3. P2 is what? 13 into 7. P3 is what? Half into 37.98 into 7. Okay, so this one will be total, it will come out as 243.3 meter. Okay, so this one is, this one is 19.5, this one is 91, this one is 32.83. Okay, now how to find out the point of application? The for point of application, what we will use, that we will use the centroid formula. So P into Y divided by total P will give us the centroid of the point of application. So P1, P1, that is area of this, P1 is acting at a height of 7 plus 3 by 3 means 8 meter from below. So we'll write 19.5 into 8. Because the centroid of this triangle is here 1 meter from here, so 8 meters from here. Again for the rectangle it is acting at 3.5, so 91 into 3.5. Then we have the last, this triangle, here we are having 7 by 3, so what it is acting at 7 by 3, so 132.93 into 7 by 3. divided by the total. What is the total? 243.3. Okay. So this will give us 3.2 ton. So the final P, so the final P is acting at a PA 3.22 meter. That's okay. This PA is acting at a 3.22 meter height from the base. So this is how we have to solve it. Okay, so this is how we need to do it. Right? Understood? Now let us see the next problem. A retaining wall 5 meter high retains a cohesionless soil C is equal to 0 with an angle of internal friction 35 degree. The surface is level with the top and the water table is below the bottom. So soil, now question of water. Determine the percentage change on the active thrust on the wall in the water table. So similar to the first problem. Right, similar to the first problem, we need to do this. So let us determine first all the required things. So first was what? Right? How much will be this? 0.271 into 5 into how much? I went to, so one more information actually it should be given, and 17 is the unit weight. 17. Right? Therefore PA is half into 5 square. This is 5 meters. Come out as now. Now what happens when the water table rises to the ground? In that case, we have K into H plus H. So PA will be will come out as 150. Percentage increase so you can see approximately 173% the earth pressure is increasing due to the submergence of the backfill soil. as the water table rises to the top, the whole backfill soil gets submerged, and due to this submergence, you can see the earth pressure is increased up to 173%. So you can see huge increase in earth pressure only because the soil is submerged. So so clearly you can see that we have to drain out the water effectively, right? We cannot allow water to stay. We have to drain out the water and the backfields also. Okay, so that's why what we do is that whenever we construct a retaining wall, we give up give required provisions. We keep required provisions so that the water is able to drain out. Whenever it rains or whatever, water is going to drain out easily from the backfields. Alright. Else you can see huge amount of water, huge amount of lateral extra lateral force. It acts on the retaining. Okay. Now see this question. A retaining wall 10-meter high retains a cohesionless soil with an angle of internal friction 30 degrees. The surface is level with the top of the wall and the water table is below the bottom of the wall. Okay. So there is a uniformly distributed surcharge of 63 kN per meter square density over the backfill. The unit weight of the backfill is 20 kN per meter cube. Determine the active pressure per meter length of the wall and its point out. So here everything is same, but here we have a surcharge that is active. Okay, so this is 10 meter and we have the PA acting somewhere at a height y. This we need to find out. So due to the surcharge, we will have some rectangular variation, right? Is nothing but Ka into Q plus, yeah, okay. So gamma is 20, K 35 degrees, so again 0.71. So P will be what? This plus this, so 0.271 into 63 into height is 10 plus half into 0.271 into 10 square into 20. So 170.73 plus 271. So you should solve this yourself, right? I am doing everything, just do it yourself also. While I do, Just to do it in your calculators yourselves and match the answers. Okay, just don't wait for me to do all the steps and just calculate everything so that you get it everything ready made. Okay, just don't wait for that. Try to solve, do everything by yourself. So before I finish, you should finish. Okay, so that you can match the answers. Right, so please do, don't just sit, please do. Okay, so we get this. Next we have to find out this point of implication y. 7 3. So this is acting here, right? The middle 10 by 2 5, 10 by 2 plus 10 by 3 5, how much? 450. So this one will give us, find it out. With 3.9. Okay, simple only, right? So let us see the next problem. A retaining wall 6 meter high retains a cohesionless soil with an angle of friction internal friction at 35 degree. G is equal to 2.7 and porosity is given 40.5%. The surface is level with the top of the wall and the water table is 2.5 meter from the top of the wall. Okay, the water table is there, 2.5 meters below the top of the wall. Determine the active pressure per meter length of the wall. Okay. So let me just draw this first. So 6 meters. So this part you are assuming dry and this is submerged, right? So this is 2.5 meter. Yeah. Now it is dry. Okay. It's like 2.6. E how to get from n? E is equal to n minus n. So from here we can get 0.66. So we get 15.7 plus submerged also. Okay. Now what is K is 0.271 since it's 35 degrees. So that we already know. Now, okay, now let us calculate. So first, top portion 2.5. So this one is parts. So number 1. So this is nothing but K gamma dry into 2.5, right? Now bottom. Okay, now first what we can do, this we can divide in two parts. So first part, so this gamma d into 2.5, that we can assume as a surcharge for the below layer. Okay, so this is number 2. This we can have K A into gamma d into 2.5. Okay, now plus, so this plus this plus this. So this is what? This is K gamma submerged into, what is the height? 3.5, right? 3. Last plus fourth one due to water. You should not forget this. Not K, sorry. Done. Now let us find one by one. What is P1? Half into K into 15.7 into 2.5 square. So this will give us P2 yes, 3.5 is the height. 3.5 is the height, and below height 2.5, 3.5. So that's why 3.5. 37.3 P3 plus 60. Then we have P4 okay, so total PA this will come out as alright, done. Now we have to find the point of application. Okay, point of application, same centroid you will use 13.3 into 2.5 by 3 plus 3.5. Okay, then we have 37.23 into 3.5 by 2. Then we have 16.37 into by 3. Then we have the amount is 1.68 meters. So finally, so if I draw, how much is it? 1.68. Quite below. Okay. This is how you have to do. Now let us come to the next problem. For the retaining wall shown in figure, find the active thrust line. So quite similar, right? So just try to solve this by yourselves. I will be back in a minute. Just try to solve this. So are you able to do this? This is quite simple, right? Almost same like that previous problem only. Here all values are also given. Just try to solve this. Okay. So just a second. Yeah. So there will be two ways. So you can see phi's are different, right? Friction angles are different for top and bottom, right? So K1 will be 1 minus sine 30 by to 0.33, and K2 similarly will be 0.271. right? And below this soil you can see it's submerged, so water table sign is there, that means it's submerged, right? So it is submerged, so let us find the submerged unit weight. Okay, rest everything is there. So let us also for the upper part, so upper half, we have this, what is this, k1 into 16 into 3. All right, now let us come. So again this will be acting as a surcharge for the below part. So it will be 16 into 3 surcharge of 16 into 3 into k2. Okay, now third, since it is submerged unit weight, so k2 into 9.19 into 3. Okay, and last is due to water, gamma w into how much, 3, right? So now what we can do, now we can calculate all the p's. p1, so same only, right? So I hope you were able to do that, just a little difference with different phi values, so k values are changing, that's all. P3 half into square, P4, so total what, p is equal to, calculate this, see how much is it, just tell me how much is it. Right, now what we need to do, we need to find the y's, y from the centroid. So first one into 3 plus 3 by 3. Okay, so this is how we need to do that. Okay, just take care of the k value, which k value you are using with which vertical stress. Okay, that is important. Others, everything is same. Okay, now let us see this problem. A soil mass is retained by a smooth inclined wall of 6 meter height. Soil has a bulk unit weight of soil has a bulk unit weight of 20 kilonewton per meter cube and a angle of internal friction 16 degree. The top of the soil is level with the top of the wall and is horizontal. If the soil surface carries a uniform distributed load and the surcharge is there, determine the total active thrust on the wall per meter and the point of application. Okay. So it's completely same, but there is a change. So I am just going to draw the diagram of the wall for you. So this is given in the question. Okay, so okay, so this is 6 meter, this is 18 degrees. Okay. Now what we can do is that this is the soil, say this is AB, and then we have this part, this is C. So this is what, this is 18 degree, so this will also be 18 degrees. Okay, 6 meter. Now let us find the earth pressure considering at this surface, this level, this imaginary straight line. Let us find it out. So first one will be what, straight rectangular one for from the surcharge plus okay, right. So now in this case, now in this condition let us find P1 and P2. So P1 will be, so let us K also we need, right? 0.568. So 4.5 0.568 into 6 P2 PA dash. Let us write this as PA dash. 15.33 plus okay. And where, what is the point of application of this? Again similarly you can find out. Now see, now what we did was, the wall is something like this. The wall is something like this. So that wall we found out the pressure in this surface, right? This imaginary surface. This straight portion we found out the this pressure. Now what we can do to find out the pressure here at the wall surface, what you can do, you can take the weight of the soil wedge, this ABC soil wedge, This ABG imaginary soil wedge. That soil wedge's weight we can take. So this weight is nothing but half into 6 is the height, and what is this? This AC into AC into 20 into 1. So AC is nothing but 6, 10, 18, 20. So this will be 116.97. So our PA dash is acting like this, W is acting like this, so P will be acting something like this. Final PA will be something like this. So how to get that? So this is at height Y. So PA is nothing but over plus PA dash square, right? Equal to 116.97 square plus 219.8 square. So this one will be 249.9 kilonewton, and this angle alpha angle is nothing but inverse A dash to. Okay, so this is how we need to solve this problem. Okay, as the wall surface is not straight here, it's inclined, we need to use this uh, technique to solve the problem. Okay, let us see the next problem. An unsupported excavation is to be made in a clay layer. The soil has a bulk unit weight of 18 kilonewton per meter cube, and just a second, yeah, and and angle of visual friction 16 degree, and C is also there. So cohesion is also there. Calculate the depth of tension crack, maximum possible unsupported depth, and we need to draw the active pressure diagram. So this is quite easy if you remember. So activity, this is sigma V. So this you already know, right? Now if we equate this to 0, as I said, we will get the depth of tension cracks. Okay, so Z naught is nothing but sorry, one thing I mistake, right? So this is, yeah, now it's fine. Sigma V is what? Z into gamma, right? Z into gamma. Z into gamma, right? So So what is n phi? Root over n phi 10 square 45 plus, so this one we can write actually twice root over gamma root over k. Okay, so this is nothing but the z naught. Alright, so therefore that is the c 18 into root over 704 for 30 for 16 degrees it's 0.704. Okay, so this is the depth of tension pipe. Alright, so k I will write here 10 by okay. Now so this is actually 10 degree. This is 10 degree. Alright, now what we need to do, next stage, it is asked calculate the depth of tension and maximum possible unsupported depth. So maximum possible unsupported depth means twice z naught. So maximum, so if tension class do not develop, what happens? As I said, the upper triangle lower triangle that cancels out, right? So it is something like this. So this upper, this and this cancels out, so this total height is twice z naught and this is z naught, right? So where depth is twice z naught. Alright, now what we are asked is we are asked to draw the active earth pressure diagram. So active earth pressure diagram is nothing but like this. So you can draw that, right? Nothing but like this, something like this. So this is nothing but twice c by n phi, and this is the this is, what is the height? So this is something like this. Okay. Minus. Okay. Now next problem, a smooth vertical wall 4 meter retains a cohesive soil backfill with a bulk unit weight of 18 kN and angular interval 0 degrees and c is equal to 10. Calculate the depth at which earth pressure is 0, means z naught. Z naught, that earth pressure is 0, right? At this depth earth pressure is 0, so that depth you need to find out. Depth of tension crack, depth at which total active thrust is 0, total active thrust per unit length of the wall, okay, and total active thrust per when tension crest do not develop. Okay, when tension crest do not develop means only the lower trapezium, that area will come. Alright, so let us calculate one by one. Depth at which first, which earth pressure is 0, nothing but z naught, k 1 minus sine 0 by 1 plus sine 0. So k is nothing but 1. Alright. Now next question is depth of tension crack. So depth of tension crack is same. That is the depth of tension crack. Now last is depth at which total active thrust when the tension cracks do not develop. Now for that, see, total height is 4 meters, right? So out of this 4 meters, so total it is 4 meters. Out of this 4 meters, this one is 1.11 meter, and below that this one is also 1.11 meter. Now tension cracks do not develop, so it means this part and this part are going to cancel out each other. So the area of this triangle, so area of this trapezium, the pressure. Now for that, what is this base? That is nothing but 4 into what is gamma, 18 into Ka. What is Ka? 1 plus 2ic by root over n phi. Root over n phi means root over Ka. So root over n phi I can write root over Ka. Root over n 1 by root over n phi I can write root over Ka. Okay, so I can write this as 2ic. So 1 by root over n phi. So 1 by root over n phi is equal to root over Ka. Okay, so this minus, right? Yeah. Root over K means minus 2ic, just minus 2ic. So this will be 52. Okay. Okay, so 72 minus 2 into 10 means 20. 72 minus 20 is 52, right? So area of trapezium, that this area of this trapezium is going to give us the active earth pressure. Okay, so what is going to be? So Pa is half into sum of parallel sides. So this one is how much? 2ic, 2ic, so 52 plus 20 or 52, and this one is 20, it's 20 into this height. Height is 4 minus 2.22. 4 minus 2. So come out as 60. And the point of application, point of action of A from bottom Okay. Okay, now let us see this problem. A smooth vertical wall 5 meter retains a cohesive soil backfill with a bulk unit weight of 18 kilonewton per meter cube and angle of internal friction 20 degrees and C is equal to 30 kPa. Calculate depth of tension crack, total active thrust per unit length of the wall when tension cracks fully developed. So now tension cracks are fully developed. Right, tension cracks are fully developed. So if you remember, if tension cracks fully developed, this is going to get considered. The area of this triangle is going to give us the total PA, right? So in that case, or in this case, what is Ka? So K is 1 minus sine 20 by 1 plus 0.49. All right. Total it's 5 meters. So this height is going to be 2ic by gamma root over Ka. So 2 into 30 by 18 into root over 0.49. So it is coming to out to be 4.76 meters. Okay, 4.76 meters. It is coming out 4.76 meters, and therefore our P, and what is this? This is nothing but gamma into height into K minus twice 2 C root over 0.49. Okay, so this will give us, therefore total PA I can get half into 2.1 into height, right? Height is 5 minus 4.76, so this will come out as 0.252 meter. Okay, so very less. All right, and after this I have one more question. This question: a smooth vertical wall 5 meter retains a soil, plot the distribution of active pressure on the wall, determine the magnitude of points of application of the active thrust, determine the intensity of fictitious individual. Okay, so this one, what if this one I am not solving it right now, what you can do is that you can do this as a homework. Okay, so this one will be homework. All right, so do this as a homework. All right, so let us see what answer you get in the next class. What I will do at the beginning, I will solve this problem and then proceed. Okay, so try to solve this problem by yourself. Okay, done. So I hope today's class you understood everything, right? So I hope you everything was clear to you, and I if there is any doubt, please feel free to contact me anytime. Okay, please free to inform me anytime. I will be more than happy to help you. And your exams are also approaching, right? So I hope all of you have, or most of you have actually registered for the exam, right? And have started preparing for the exam. So please study nicely. And if you have any doubts, please feel free to ask me anytime. I will be more than happy to help you. And as I said, our next session, next live interactive session or live discussion session will be on 5th of April from 6 p.m. to 8 p.m. the same time, 5th of April. So let us meet on the 5th with the 12th, sorry, with the 11th discussion session. And I am hopeful that today's discussion session was fruitful to you. And if please solve these problems again and try to match the answers, practice more and more. And if you have any doubts, please feel free to contact me anytime. Sorry, please feel free to contact me anytime. Okay, so thank you for attending and have a very good evening. Okay, thank you.